Okay, so today's lesson we're going to be talking about the concept is this is our second advanced integration technique, right? We talked about integration by parts. That was our first sort of advanced integration technique. We've already done use substitution, so we've got those two under our belt. This is the third one. It's integrating using partial fractions. So what we're doing today is we're going to start with this lesson is focused on decomposing rational functions into their partial fractional parts, okay? And so in order to do that, I need to kind of start from scratch. So why are we doing this? A rational function integrand that cannot be easily integrated by use substitution, which we've covered in Calc 30, or by parts, so integration by parts, which was that DI method that we just did, could sometimes be integrated easily by decomposing the rational expression into its fractional parts, or using partial fractions. So if you look up integrating partial fractions or integration partial fractions on the internet, you'll find lots of stuff on this. So that's what we're going to talk about here today. So the big idea here is to get rid of the x's in the numerator, or the sort of polynomials with x terms in the numerator, to get rid of those and to split them up into numerators that have constant numbers. Okay, that's the thing. The predictable process of decomposition is the basis of this lesson. So let me just set this up for you before we get into this example. But if you have something like 3x squared plus 2x plus 1 divided by x plus 2, okay, if use substitution doesn't work and you've got this nasty kind of quotient, it's not real easy to do. And the DI method by parts might not be very easy either. Might be pretty messy. So what we're going to try and do is we're going to try and get, this is what we want to end up with. And you see this example, we're going to simplify it. We're going to combine this. But if we have to integrate something like this, 1 over u is easily integratable, right? So that's the whole point. That's the big picture. We're going to try and split complicated rational functions into partial fractional parts. So the first place I want to take you is simplifying this. And this is old school stuff. This is stuff you've been doing for years and years and years. So when we simplify this right here, what we're going to want to do is get a common, what? Denominator, right? So what we're going to do is we're going to multiply top and bottom by the factor that it doesn't have. And this is going to be x plus 3 plus 5x plus 2 all over our now common denominator of x plus 2 plus x plus 3. So we now distribute and gather like terms. So this is going to be 5x plus 10. So we're going to have x plus 3 plus 5x plus 10 all over our denominator here. When we combine those the like terms on top, we get 6x plus 13 over x plus 2 times x plus 3. So what this means is, now we've simplified this original question. So what this means is that this rational right here, which would be pretty difficult for us to integrate, remember, the goal is to try and find a way to do that. So that's pretty tough to do. Use substitution, we've got multiple factors down here. What's u? Can't do it. But if we can somehow now go from this complicated rational back to this original question, if we can split it into its fractional parts, if we can somehow figure out an algorithm to do that, a method to do that, that's going to help us out a lot. So that's what today's lesson is about. We're going to do that. We're going to split this into its fractional parts. So decomposing a rational fraction is the reverse process of what we just did. And if we have a function, okay, in the numerator, and we have factors okay, binomial factors in this sort of pattern, and again, there's lots of different rational functions, right? And we're going to take a look at how to decompose just a couple of types. So again, this is university level stuff, but this is the basic, this is the introduction to it. So that's what we're doing in this advanced integration course in high school here. So this will be a good launch pad when you get into calculus 2 or whatever in university, when you actually do more of this stuff. So this is the pattern. There is going to be a fraction with a constant numerator, and over a over x plus a plus b over x plus b. So this is predictable. Now, a little caveat here: the degree of the numerator has to be less than the degree of the denominator in order for this to work. And again, this is where this doesn't happen. That's one of the many cases that there would be a slightly different method for. So as we see in this example, and this is our example that we just did, right? You might see something like this, and you would notice that the degree in the numerator is 1, and the degree in the denominator is 2. You would also see that this is easily factorable, so this would be a candidate for decomposing into partial fractions, and you would use this right here. So what we're going to do now is we're going to go backwards, and I'm going to show you two sort of methods. There's going to be kind of a method of doing this, and there's going to be two important parts that we want to learn about in this lesson. So let's do this. Let's take this, and let's try and get back to the original question, which was 1 over x plus 2 plus 5 over x plus 3. Let's see if we can do it. Okay? So the first thing you're going to want to do is you're going to want to express this numerator as binomial factors if you can. And that's what we want to try and do first. So factoring this is pretty basic. The two numbers that multiply to 6 and add to 5. So that's x plus 2 and x plus 3. Okay? So we know that that is just another way to write that actual question. Okay. So the format is this: 6x plus 13 over x plus 2 times x plus 3 should equal this: a, some number, numerator, over one of these factors, plus separately another constant numerator over the other factor. Okay, we know that this exists. Under these criteria, the degree on the top is less than the degree on the bottom, and we have two separate factors. And we can do this with 3 or 4 or 10 factors too. The format is the same, but this is how we're going to do this. So what we want to do is we want to solve for a and b. Now we have a lot of unknowns, right? So how do we do that? Well, first of all, let's multiply everything by the two factors that we have on the bottom. So that's going to give us 6x plus 13 on the left side. That's going to give us a times x plus 3 right here, because the x plus 2 divides with the x plus 2. And we're going to have b times x plus 2 here. Okay? So we want to get rid of the denominators, and we want to start to deal with this as a bit of a polynomial. Okay? Okay, so this is where it diverges a bit. Once you get to this easy spot here, this is where the methods diverge just a little bit. I'm going to show you both ways to take it from here. Okay? So the first method is by substitution. Okay, so we're going to substitute values. That's sort of the first way to take it from here. So what would happen to this if we let x, and we're going to just substitute different values for x, what if we let x equal negative 3? Okay, what would that look like? Well, we'd have 6 times negative 3 plus 13 equals a times negative 3 plus 3 plus b times negative 3 plus 2. Simplifying this, we have negative 18 plus 13 is negative 5. and we have a times 0, and we have b times negative 1. Now, why did I choose x equals negative 3? Why did I choose that? Can I see that? Sorry? Yeah, to take out a, right? Because a is now gone. It's nice to be able to solve for just b. So, negative 5 equals negative b, so we have b equals 5. Okay? And similarly, we can solve for a by doing the same thing. We can, over here, let's let x equal what? If I look at this row right here, if I want to get rid of b now to isolate a, I can let x equal negative 2. Right? I could do that as well. And so this is what this looks like over here. And again, there's different algebraic sort of tricks you can do, but substituting values. You can even let b equal 5 as well if you want, and x equal, whatever you want, and b equal 5, and then you can go that way because we already know b is 5. But here's following the same method. So x equals 2 is going to get rid of negative 2 is going to get rid of this b value. So we're going to have 6 times negative 2 plus 13 equals a times negative 2 plus 3 plus b times 0. So negative 12 plus 13 is 1. Negative 2 plus 3 is 1. So we have a times 1 plus 0. So a equals 1. Okay? So, if we look at this now, if we go back to our original question, which is this part right here, guess what? A is 1 and b is 5. So if we would take the opportunity to rewrite that, we would have, and you don't have to do this if you don't want to, I'll just kind of show you, equals 1 over x plus 2 plus 5 over x plus 3. Okay, and that's how we find those coefficients. And that's way back here, that's where we started with. See, 1 over x plus 2 plus 5 over x plus 3. So this is all the same question. We're going kind of forward to expand and to combine, and now we are decomposing. So we get the same values. Okay? So substituting values, that one's pretty easy. If you have multiple factors that are different, if the factors are repeated, that's going to be type 2 we're going to get to in a bit. But if you have multiple binomial factors that are different, then you're going to have a over the first factor plus b over the second factor plus c over the next factor plus d and so on. So it's just a bit of a pattern there. Okay, so here is the next method. Let me just make some more space here before my next example. Okay, so the next kind of method is called equating coefficients. And you can use one or both of these methods to solve for unknowns. You can also add simultaneous equations, different things, but these are the two big ones. So what do I mean by that? Well, remember back here when we had, somebody doesn't sound happy out there, we had 6x plus 13 equals a times x plus 3 plus b times x plus 2, right? So in this one, what you want to do is you want to expand the right side. You don't have to substitute any variables here just yet. You want to expand the right side. So this is going to be ax plus 3a plus bx plus 2b. Okay? And then we're going to rearrange a little bit. So we're going to get all the x terms together. So it's going to be ax plus bx. And we're going to get, now remember, a is a constant, so these are constant terms. 3a and 2b are constant terms. So we're going to just kind of move those together. Okay? One more step, and you'll see why I do this step in a minute. One more step. I'm going to factor an x out, and I'm going to write this as a plus b times x. And over here, it doesn't, you don't have to factor anything out, but what I'm going to do is just put some brackets around these two terms because they're all added. Okay. So, what we can do is notice that on the left side of the equation, we have an x term. Okay. I think this is kind of cool, actually. I think this this is kind of neat. We have an x term over here, and on the right side now we have an x term. Okay. We also have a constant term, and over here we have a constant term. So, without substituting anything yet, what we can see is that a plus b has to equal 6. So 6 equals a plus b, because we're equating the coefficients of the polynomials on both sides. And then we also see that 13 has to equal 3a plus 2b. Okay? So working with these two simultaneous equations, you can do all sorts of things. You can add the two equations together. Okay, you can do some substitution. You can solve for b on this side, let's say, and put in 6 minus a over here. So you can do all sorts of things. So elimination, substitution, remember we learned back in grade 10 a couple years ago. So I'm going to do that. I'm going to go b is 6 minus a, and I'm going to substitute that in here. So then we just go ahead and complete that, expand everything out. So plus 12 minus 2a, 3a minus 2a is 1a. Subtract 12 from both sides, we get a equals 1. And then of course from there, with a equals 1, you can now find out what b is. You can go back to this first one here, and go 6 equals 1 plus b. b is 5. So I don't know which one of those two methods you like better, but those are the two kind of main methods that we can use to solve for constants. Okay? Any questions so far? Okay? So there's one example. Really just did one example there for you. So I'm going to start you on the next example, and I'm going to see if you guys can finish this off. Okay? So this one here, let's say that this one we want to decompose this one. Again, we have an x in the numerator and x is in the denominator, but we do have this factored. So I have two separate factors, so guess what? This should come out to some constant over our first factor plus another constant over our second factor. So that should be the format from what we know. So in order to do that, of course, we're going to multiply both sides by the factors. The common factors are the two factors on the left. Okay. So when you get to this stage, so now I want to see if you guys, from what you know, go ahead and see if you can solve for a and b here. Okay. And I'll freeze the screen. I'll show you my work in a minute. So I chose to do the substitution method here, and what we have is we have a being 2/5. If you let x equal 2, you can solve for a, and that should be 2/5. If you let x equals 3, it looks like b should be negative 3/5. Okay, you get that? No? You got 8/5 and negative 3/5? Okay, let's see if we can figure out where you went wrong there. Did you do substitution? Oh, you equated? Okay, I tell you what. Why don't we just do that real quick? You equated the coefficients, okay? Okay, let's just see here. So what you did, I guess you expanded this out. So we have x equals, we have ax plus 3a plus 2b minus bx. Okay, so then we've got x equals a minus b times x, right? We can do that together, and then plus 3a plus 2b. Okay, so a minus b has to equal 1. Okay, but let's just see here. So we've got 3a and 2b x. So we've got 1x here and then plus 0, right? So is that what you did? Okay. So you've got a minus b equals 1. Okay. And then over here you've got what? 3a plus 2b equals 0. So again, so we've got the coefficient of the x term, which over here has to equal 1, and then the constant has to equal 0. So reconciling these two, let's see. Let's solve for, I don't know, a is 1 plus b. And so we have 1 plus b plus 2b equals 0. That's 3 plus 3b plus 2b equals 0. So 5b is going to equal negative 3. So b is negative 3/5. Okay, so did you get that? Okay. Okay, great. So let's take a look at, whoa, I've got a random b there. So then, oh yeah, I guess all we need to do here now is to find out what a is. So a is 1 minus 3 over 5. So it would be 5 over 5 minus 3 over 5. So a is positive 2/5.
But wouldn't it be a equals 1 plus? Oh.
B is negative 3/5. Yeah. So you just added 5 and 3 instead of subtracted? Okay. All right. Okay, so that's great. That's the two different methods there. Just a little algebraic error, no problem. So this is the big thing here now, to rewrite this. So let's look at the 3 steps here that I've shown. So, oh yeah, that's where my b was. So obviously this is what we started with, right? X over 2 minus x times x plus 3. And the a and the b we found to be 2/5 and negative 3/5. So how you write that is this. It's obviously a is a fraction, so what you do is you put 2 up here and a 5 down in the numerator. Yeah. Minus, because it's a negative, minus 3 over 5. So this is your final answer.
Should you expand the denominator or just leave it?
You could expand the denominator. You wouldn't have to. No. No, at this point you can just leave it like that. Yeah. Okay. So any questions on that one? All right. So the key to this is practice. I've got one more there, and this is type 2 here. We're going to talk about that next lesson. So why don't you give this a crack right here. Okay, you guys do that. And again, I'll show you sort of what the answer looks like in a few minutes. So let's take a look here. This is going to be equal to 3 over x times x plus 1, right? So we have our 2. So if we know that, then that's going to equal a over x plus b over x plus 1, right? You get that far? Okay, good. So we have 3 equals a times x plus 1 plus bx, correct? So 3 equals ax plus a plus bx. Now, if we do our equating coefficients method, that's no problem. We've got 0x over here, sorry, plus 3, right? And over here we've got a plus b x plus a. So I know what a is right now. A is 3. Look good? And a plus b is going to equal 0. So we've got 3 plus b equals 0. So b looks to be negative 3. And I'm doing this as fast and messy as I possibly can. So did you guys get that? Okay. So then to rewrite this, right, we're going to take this right here, and we're going to fill in our values for a and b. And of course, you would at least, rewrite. You don't have to rewrite the question over again, but you should have this written out as in your answer. So obviously this is going to be equal to 3 over x plus, or let's do a minus there, minus 3 over x plus 1. Okay, does that look right? You guys look good? Okay, so we could check this, right? I'm not making you, but of course we could check this by adding these two up like we did before, and to see if you get 3 over x times x plus 1. So I won't bother you with that, but get common terms here, common denominator, sorry, and then combine. Okay? So that's going to be 3x minus 3x plus 1. So it's going to be equal to that. We're good. Questions? Okay. I do have some questions for you to work on for practice. Okay, so for this lesson here, what you can do is you can do some practice on your own by doing question number 1 from your assignment. So I think with this period we're going to talk about type 2, but for the first part of this lesson, number 1 are your practice problems. And here they are.